Okay, so we've talked about some of the laws relating the different variables of gases to each other. We had Boyle's law, which relates volume and pressure to each other, saying volume is inversely proportional to pressure. We've got Charles' law, which states that volume and temperature are directly proportional, and you've got Avogadro's law that states that volume and the number of moles are directly proportional. But it would be nice to be able to have one law that puts all three of these variables together, the volume, the temperature, and pressure, and then also the number of moles. So to be able to put all four of our variables into one law. And if we just combine these laws, we could say at least that the volume is directly proportional to the number of moles and temperature, but inversely proportional to pressure. But I can make this a little bit more concrete if I include a proportionality constant. This is known as the gas constant, R, and this allows me to actually write volume is equal to R times the number of moles of the gas times temperature divided by the pressure. Now, the actual value of R is a little bit dependent on its units. So whether I have pressure in atmospheres or in torr, that's going to affect the numerical value of the gas constant. We have a small table here, and when selecting which R value to use in a particular problem, it's generally a good idea to look at the units of the pressure. Because if we have atmospheres, we'll probably want to use this top equation, or this top R value, whereas if we've got it in torr, we might want to use this bottom case. Now, this equation here that's been written, if we multiply both sides by P, if we rearrange it slightly and bring the pressure out so we don't have any fractions, we get to something that's known as the ideal gas law. So that's the pressure times the volume is equal to the number of moles times the gas constant times temperature in Kelvin. And this is known as the ideal gas law because it describes gases behaving in what's sort of, quote, an ideal manner, the normal manner where we make two assumptions in order for a gas to fit the ideal gas law and behave ideally. And those two assumptions are, first, that the molecules of an ideal gas do not interact. They behave entirely isolated from each other. They don't feel the presence of any other gas molecules. And that's very important for a gas following the ideal gas law. We'll see later on that this is not always the case, and we'll have to amend our law to account for that. And then second, that the volume that's occupied by the actual molecules of the gas is much, much smaller than the volume occupied by the total gas. So that is what we mentioned earlier, where normally gases occupy a tiny fraction, maybe 0.1% of the total volume that they occupy. The actual molecules, the volume occupied by the molecules is a tiny fraction of the volume that the gas as a whole occupies. And that's important as well, because if that is not true, then we tend to have interactions between gas molecules, and this equation will no longer hold for most gases. So this is an extremely useful equation, PV equals nRT, because it now relates the four variables to each other. So let's see an example of how we might use this in a problem. So a Goodyear blimp is filled with hydrogen gas to a volume of 8.43 times 10 to the 6 liters. The pressure inside the blimp itself is very low at 0.00500 atmospheres. What is the mass of hydrogen gas inside the blimp if the temperature of the system is 20 degrees Celsius? Well, so we have a gas, hydrogen gas, in a Goodyear blimp. I think nowadays they use something else due to the flammability of hydrogen, but as just an example here. So we know pressure, so we know P, we know our volume, so we know V. We know our temperature here in Celsius. We'll have to convert that to Kelvin. And we can choose an appropriate gas constant. So the only thing we don't know is the number of moles. Once I've solved for the number of moles, then I can convert from moles to mass using the molar mass of hydrogen. So here, when I'm choosing a unit for R, or a value for R, I'm going to want to pay attention to the units of pressure. So pressure is in atmospheres here. So I will choose this top case, the 0.08206 liter atmospheres per mole Kelvin for R. So if I rearrange to solve for N and then substitute these values in, I substitute in my pressure, volume, my R value, and I convert my temperature to Kelvin and substitute that in. This way, the Kelvin will cancel, the atmospheres will cancel, the liters will cancel, and I'll be left only with moles. And I come out with 1,752.17 moles of hydrogen. At this point, I'm not worrying about significant figures. Now that I have number of moles of hydrogen, I can convert that to mass of hydrogen using the molar mass of H2. And so then I come out with 3,539.38 grams of hydrogen. Now I have to watch significant figures. Up in this equation, I have only 3 significant figures for a couple of these, so I'm limited then to 3 significant figures. And I decide to convert from grams to kilograms simply by dividing by 1,000. So that will give me, if I round this out to 3 significant figures, 3.54 kilograms of hydrogen. And that's how I can use those variables to determine an unknown variable for a gas. Now let's keep talking about the ideal gas law a little bit. There's a few other definitions that we should include and cases to mention that fall out from the ideal gas law. So the first is this term standard temperature and pressure, or STP. This is a good reference value, and often values in the literature reported at STP or reference to STP. And that definition is just, what is standard temperature and pressure? Well, standard temperature is going to be 0 degrees Celsius, 273.15 Kelvin. That's more of a standard temperature. You might think that's not very standard. We don't normally live at 0 degrees Celsius. True, but all throughout the world, a standard daily temperature, even in Celsius, may vary widely. And so 0 degrees Celsius is a good benchmark for this. And so this is set to be standard temperature. Standard pressure is set to be 1 atmosphere. So this is ideal atmospheric pressure at sea level. And with that information then, we can use the standard temperature and the standard pressure to calculate the volume of 1.0 moles of an ideal gas at standard temperature and pressure. And simply by taking the ideal gas law, we're solving for volume here, so we divide both sides by P. Volume is equal to nRT over P. We know T and P and N is 1, and we substitute in for R. Using the appropriate gas constant, we're using atmospheres for pressure. So here we use this the top value for R. Substitute those values in, and what we find is that 1 mole of an ideal gas should occupy 22.41 liters of volume. And this is useful because it's a measure for how ideal actual gases are, because we can take 1 mole of an actual gas and measure what volume it occupies at temperature, at the standard temperature and standard pressure. And we can see a few of those shown here. So an ideal gas should be at 22.41 liters. And many normal gases, such as carbon dioxide, are very close to that. Carbon dioxide, nitrogen, helium, hydrogen, all of these are very, very close. Helium is actually a perfectly ideal gas. And then we can also see other gases that deviate from that some. So chlorine gas, for example, is a little bit less of an ideal, slightly less of an ideal gas. And we could do this for other gases as well, and have a measure for how ideal a gas actually is. Now, one more thing to go with all of this. So say that we have a set quantity of an ideal gas, and the pressure and volume and temperature all change. So we're under one set of conditions, and then we enter a case where all of those change. The pressure, the volume, and the temperature all change. So we've done small examples of this when we were doing Boyle's, Charles, and Avogadro's laws, but we didn't do, I guess just Boyle's and Charles' law, but we didn't do all three together. So we can take the ideal gas law, and we can note that if we have a set quantity means that N, or the number of moles, is constant. Now R is already a constant, so we can rearrange this equation to have pressure volume over temperature is equal to N times R, and if N is held constant, then this is just a constant. And so what we can write from this then is something known as the combined gas law, which is just that pressure under one set of conditions times volume under one set of conditions over temperature under one set of conditions is equal to P2 V2 over T2. And this is extremely useful for a case where the amount of gas is not changing, but the other variables are. So let's go through a quick example of this. Let's say you have a party balloon that has a volume of 1.2 liters at sea level. So we're at 1 atmosphere there. And that's let go to rise up through the atmosphere. And it rises until the pressure is 0.31 atmospheres. And the temperature in the atmosphere also changes, and it's dropped from 22 degrees Celsius all the way down to negative 25 degrees Celsius. So what's the final volume of the balloon? So we have a set quantity because presumably none of the gas is escaping from the balloon. So however much gas is in the balloon, that's staying constant. So we can use our combined gas law here, and note that what we know is we know pressure 1, we know volume 1, we know temperature 1. All of that stuff's given to us. We need to convert temperature to Kelvin in order to be able to use it. And then we also know our pressure 2 and our temperature 2, which must also be converted to Kelvin. And that's crucial here because we have a negative sign that would give us a nonsensical value for our volume. So after we've converted those, then what we're really just looking for is volume 2. So we do a little bit of rearranging, a little bit of algebra, multiply both sides by T2, divide both sides by P2, and now we get P1 V1 T2 over T1 P2 is equal to V2. And then you substitute the values in, and we come out with a volume of 3.3 liters for that party balloon. So that's how we would use the ideal gas law kind of rearranged to the combined gas law to solve for variables where all three, the pressure, the volume, and the temperature are changing, but the amount of gas is not changing.